This video introduces a solution that easily measures the conductivity of copper foil and metals used in substrates for millimeter wave technology up to 170 GHz. With technological innovations beyond 5G, copper foil used in circuits like high-frequency substrates and antennas requires high conductivity even at high frequencies. Conductivity is a critical parameter directly affecting transmission and antenna performance, but it degrades in the millimeter wave band due to the skin effect. Particularly, copper foil subjected to roughening treatment to improve adhesion with resin is significantly affected by the skin effect, resulting in decreased conductivity at higher frequencies. In other words, since conductivity has frequency characteristics, measurement at the actual operating frequency is crucial. Conductivity measurement methods include measuring transmission characteristics using microstrip lines or using dedicated conductivity measurement devices. However, evaluating transmission characteristics via microstrip lines was time-consuming to fabricate, yet only yielded conductivity values that included fabrication errors. Furthermore, conventional conductivity measurement devices often had a poor reputation, low measurement reliability and reproducibility, cumbersome operation, and difficulty in obtaining frequency characteristics. The measurement device introduced in this video is a groundbreaking solution that resolves all these issues. This time, we introduce a device capable of measuring conductivity across the 23 GHz to 110 GHz range in a single measurement, encompassing frequencies used in 5G, AI servers, and automotive radar. Direct and accurate conductivity measurement significantly enhances simulation precision, undoubtedly boosting development efficiency. The video also demonstrates reproducibility, so please watch until the end. Let us first explain the equipment used for measurement. Keysight Network Analyzer, Extension Modules, Control PC and Conductivity Measurement Software. EMlabs Fabry-Perot Resonator for conductivity measurement. This is the basic setup. Stable measurements can be performed even when placed on an ordinary workbench. EMlabs Fabry-Perot Resonator for conductivity measurement comes in two types. Broadband model covering from 23 to 110 GHz. A D-band model covering from 110 to 170 GHz. In this video, we will demonstrate measurements using the broadband model, which includes the frequencies used in 5G and automotive radar. The basic operation is identical for all bands, only the frequency range is different. First, let's install the device. Simply connect the 1 mm cable using a torque wrench. No calibration is required. The measurement covers 35 points at 2.5 GHz intervals between 23 and 110 GHz. The test sample used here is raw copper sold for high-frequency applications. Here is a brief explanation of the measurement procedure. First, we measure the reference copper. Next, we set the sample and perform the position adjustment. Finally, all frequency points are measured automatically in sequence. This video demonstrates every step in the process. All measurements are performed using the dedicated conductivity measurement software. This is the main screen of the software. It includes sample information registration, various operation buttons, conductivity measurement results, and a graph that clearly shows the frequency characteristics. Now, let's measure the reference copper. First, set the reference copper onto the dedicated clamping plate and insert it into the resonator. Tighten the screws, close the lid, and the setup is complete. Start the software and select the frequency of the resonator being used. Pressing the reference measurement button automatically controls the network analyzer and proceeds with the measurement. The system first checks the device stability. Once the stability reaches 100% and sufficient stability is confirmed, the software begins measuring the resonance points sequentially at 2.5 GHz intervals. At the 75 GHz region, it is necessary to pull out the band selector. Follow the instructions shown in the software pop-up. Measuring all frequency points takes approximately 3 minutes. Now we move on to the sample measurement. First, mount the sample. As with the reference copper, place the sample on the clamping plate and insert it into the resonator. The copper foil or substrate to be measured should be pre-attached to a dedicated glass plate. Attach the cover for stability to complete the sample setup. Press the Sample Position Adjustment button to begin adjustment. While watching the screen, slowly turn the knob so that the trace falls within the dotted lines. The upper right corner of the adjustment screen indicates the direction in which the knob should be turned. Please follow these instructions. When the position adjustment is complete, press the Finish button. The software then checks whether the sample is stable. Once stability is confirmed, the system automatically proceeds to sample measurement. Band selector operation is again required around 75 GHz, and this operation is needed for each measurement. From 110 GHz onward, the system automatically measures the resonance peaks, and the results are displayed as both numerical values and graphs. The measurement takes about 3 minutes. For reproducibility verification, we measure the same sample 3 times. If you simply press the measurement button without touching the sample, you cannot observe the true measurement error of the device. Therefore, for proper reproducibility evaluation, the sample is inverted, top and bottom reversed, before each measurement. As you can see, even after multiple measurements, the system demonstrates extremely high reproducibility. Please note that in conductivity measurements, the higher the conductivity, the more difficult the measurement becomes. Therefore, when evaluating the device accurately, it is recommended to refer to measurement examples with a relative conductivity of 0.6 or higher. In many cases, the goal is not simply to measure the conductivity of copper foil alone, but rather the interface conductivity between the copper and a dielectric material. When copper is deposited onto resin by sputtering or evaporation, measuring the interface conductivity with the dielectric becomes essential. EMlabs Fabry-Perot Resonator for conductivity measurement is capable of performing such measurements. Here, we prepared a sample by bonding polyimide, a dielectric material, onto the copper foil we measured earlier. For accurate conductivity evaluation, information on the dielectric's thickness, permittivity, and dissipation factor is required. Since permittivity also has frequency dependence, entering values at multiple frequencies leads to more accurate results. Permittivity information can be entered from the sample settings screen. The polyimide used in this example has a thickness of 60 micrometers. Measurement results obtained using EMlabs Fabry-Perot Resonator for dielectric measurements can be imported easily. The measurement procedure that follows is the same as for copper foil alone. Now let's take a look at the measurement results. There appears to be no change in conductivity caused by bonding the dielectric layer. In this way, the interface conductivity, with and without the dielectric material, can be compared easily. Measurement results can be saved as Excel files using the export function. How was it? Conductivity in the millimeter wave range, which previously could not be measured stably, can now be measured with ease. With measurements this simple and stable, selecting copper foils with higher transmission performance or better antenna performance becomes much more straightforward. If you need more detailed information, please contact EMlabs. For those who wish to have their samples evaluated immediately, we recommend our contract measurement service.